Our last topic for Unit 11 is exponential and quadratic regression. So we'll start with exponential regression. Exponential regression will be in the form f of x equals a times b to the x. A is your initial value, or your y-intercept, and b is your base. That is your growth or decay factor. It is what you are repeatedly multiplying by. Remember that an exponent exists because of repeated multiplication. Anytime your base is larger than 1, that means that it is growth. And anytime it is between 0 and 1, that means you have decay. What you'll need to find will be your percentage that you are growing or decaying by. And so you'll use one of the two formulas depending on if you have growth or decay. So if you have growth, you're going to use b equals 1 plus r. Again, b is your base. For growth, that would have to be larger than 1. And r would represent the rate that it's growing by, and that can be turned into a percentage. So if you were growing by 5%, 5% is 0.05, that would be your r, and 1 plus 0.05 would be 1.05 for your base. If you were decaying by 5%, again, 5% is 0.05. 1 minus 0.05 would be 0.95 for decay. Exponential regression does not have a correlation coefficient. For our first example, we are looking at the number of Starbucks that have been around since 1971. Anytime you have years, you really want to take that first year and make that your year 0. Because what you don't want to try to do is graph 1971 along the x-axis. So what we're going to do is we're going to call 1971 year 0. And then we're going to find the years since 1971. So 1987 is 16 years away from 1971. 1991 would be 20 years. 1996 minus 1971 is 25. 2001 minus 1971 is 30. 2006 minus 1971 is 35. 2011 minus 1971 would be 40. 2015 minus 71 would be 44. And then finally, 2018 minus 1971 would be 47. So what we are going to do is we are going to graph the years since 1971 along our x-axis, and then our number of Starbucks is going to go on our y-axis. So I'm going to try to label these. So years since 1971, and then again, number of stores on the y-axis. All right, so I'm going to do my best to graph these. It looks like, 9 points right now. So 0, 1 is going to be pretty much just the origin. I'm going to use this kind of tool to mark the points because when I try to do it with a pen and do a circle, it doesn't work very well. 1987 was year 16, and there were 17 stores. So I'm going to jump to 16 along my x-axis, and 17 stores is really going to be pretty low. It's not really going to be a jump at all. After 20 years, we have 116, so maybe you see a little bit of a jump, but not much of anything. 25 years, we have 1,000, so almost halfway up, but not quite. 30 years, we have 4,709, so just below 5,000, so we can see actually some movement there. 35 years, we have 12,440, so definitely a lot higher this time. 40 years, 17,000, so about right here. 44 years, 23,000. So let's call it about right there. And finally, just under 30,000 after 47 years. So we're looking about, let's call it right there. So at first, when we graphed all the way up to 25 years, you really couldn't see what's going on. But now that we have those last few points, I think you guys can see that this is indeed exponential growth because it's growing quite quickly after it hits that 25-year mark. So this would be exponential. For what type of function does it represent? And you can give a couple different reasons. You could say it's a J-curve, growing quickly, not growing at a constant rate of change. There are, several different explanations that you could use. I'm just going to say growing quickly. All right, so let's see, what do we do with this? One of the things you're going to need to be able to do is to look at a scatter plot and identify if it's linear, exponential, or quadratic. So hopefully when you see that graph, that definitely looks exponential to you. All right, so for C, it says the exponential equation for this data is best modeled by the function s of x equals 1.2 times 1.27 to the x. What is the annual percentage of growth for Starbucks according to this model? So the annual percentage is going to come from the base, which is 1.27. Because that base is larger than 1, we know it's growth. We also know it's growth because our graph and our numbers were growing. But the equation that you use for that is b equals 1 plus r. And in order to find the percentage, we need to first find r. Well, we know that our base is 1.27, so I am going to put 1.27 in the place of b, and I am going to solve for r. So to solve for r, we're going to subtract 1. So r equals 0.27. And as a percentage, to change that to a percent, you're going to take the decimal and you are going to move it either 2 spots to the right, or you're going to multiply by 100. It's your preference. They mean the same thing, but that will give you 27%. So with these data values, what it's showing is that Starbucks were growing by 27% per year. Now, I think if we were to look at that now, maybe if we looked at it in the past 5 years, you probably would not see as large as of a percentage for growth because there are Starbucks everywhere now. So we're still seeing more added, but they're not growing as quickly. Whereas when we started with 1, so obviously we've seen a lot of growth. D says, according to the model, what is the y-intercept? The y-intercept is given to us by A, which is 1.2. So what that means is that the y-intercept is where it starts, so that would be year 0. So according to this, it says at the 0 year or in 1971, oh, let me switch my pen here. So in 1971, there was 1.2 Starbucks. So obviously you can't have part of a store, so that 0.2 doesn't really make sense, but we do know in 1971 we started with 1, so that 1.2 is actually pretty close to our actual starting value, which is good. Sometimes it's not as close, so this one is really close to what we actually had. So the last part for this problem says predict the number of Starbucks in the year 2025. So in order to do this problem, we need to figure out how many years have passed from 2025 to 1971, because X is representing our years since 1971. So to find X, we're going to do 2025 minus 1971. And if we do that, that should be 54. So we are going to substitute 54 in for X into our model. 1.2 times 1.27 to the 54. And then obviously you would just use your calculator or Desmos for that. You're not going to try to calculate that by hand. I don't think anybody would want to do 1.27 to the 54 on their own. And let's see what we get. All right, I got 483,700, and it says 6.783, and it keeps going. We can't have part of a store, so we're just going to round that to the nearest whole number. So we're going to say 707 stores. And that is assuming that this rate continues. Like I said before, probably not going to keep growing at 27% increase per year. The last type of regression that we have is quadratic regression. So this would be when you graph data and you notice that U-shape or parabola shape to your scatter plot. We will have our regression be in the form of f of x equals a times x squared plus bx plus c. So that would be standard form. If your a value is positive or larger than 0, then your parabola will be opening up. Whereas if your a value is negative or below 0, your parabola would open down. You can find your axis of symmetry by using the same formula we used back in Unit 7, so opposite b over 2a. And then if you want to find your vertex, you would just plug in whatever you get for the axis of symmetry back into the equation. That will give you your y-coordinate, which would make up your vertex. So remember that your vertex has the same x value as your axis of symmetry, and then you plug that number in to find the y-coordinate. Your y-intercept will be given to you. You can plug 0 in for x, but if it's in standard form, the y-intercept is the c value. And again, no correlation coefficient for quadratic regression. That correlation coefficient only exists for linear regression. So in this particular example, we are looking at the horizontal distance that a baseball travels when it's hit at different angles. So when you, with your bat, you hit the ball at different angles, we're seeing how, if that impacts how far the ball travels horizontally. And that's assuming that the speed, like, is the same in which you're hitting the ball every single time. So we're going to graph this and look at the shape of the graph, and then we'll be given the function and we'll do some things with the function. So here we go. Again, the graph is a little bit tricky to do on this, so I have to, it's going to look a little funky, but I'm going to do my best to get it pretty good. So at 10 degrees, the ball is 116 feet. So I'm going to go over to 10 on x and about 116 on y. All right, then at 15 degrees, we have 157. So about right here. 20 degrees, 189. About right there. 24 and 221. So it's a little bit over. Let me try that one again. Okay, 24, 221. Okay, about right there. 30 is 254. 34 is 269. About right there. Then at 40, we have 285. And then also at 45, 285. 48, it's starting to come back down a little bit, so that's 277. At 50, 269. 58 is 244. maybe about right there. That's not the best one, but it's all right. 60 is 231. And finally, 64 degrees is 180. Right, so hopefully when you look at that, you see that it starts low, goes up, hits a maximum, and comes back down. So this would be representative of a quadratic function because it has that parabola or U shape to it. So quadratic, and you can say that it looks like a parabola, has a U shape, goes up and comes back down. There's a lot of different ways that you could explain why you chose quadratic. On C, they give us this equation, d of x equals negative 0.17 x squared plus 14.52x minus 21.79. That is our regression function. There is a way to use your calculator and type in all those x coordinates and all those y coordinates, and it will actually come up with this equation for you. But we're just going to go ahead and give it to you. This question says, why should A be a negative number? So A is that very first number, that negative 0.17. And if you go back to that previous slide that we were just talking about, when A is negative, the parabola opens down. So since this parabola opens down, A should be a negative number. So why should it be a negative number? The parabola opens down. All right, let's see what else we got. So this is going right along with the same thing. It says, according to the model, what is the y-intercept? Does this make sense? So again, going back to that first slide where we gave you the details of the quadratic regression, the y-intercept is where x is 0. And if you were to plug 0 in for both of your x's, that would leave you with the c value. So our y-intercept is the c value. So according to this model, this equation, our y-intercept is negative 21.79. Now what that means in the context of the problem is when you hit the ball with a 0-degree angle, it would travel negative 21.79, I think it was feet, yes, which the ball can't travel negative 21.79 feet. If you hit the ball with a 0-degree angle, it's not going to go backwards. So that doesn't necessarily make sense to have a negative distance. So negative 21.79, and so no, you can't have negative distance, or the distance shouldn't be negative. I'm just going to say the distance shouldn't be negative. Now, the reason we got a negative value is because according to the model, like, if you're just looking at the numbers, you're not looking at the context of the problem, it would hit the y-axis below 0. And so according to those data values, that's what it should be. But according to our scenario, that does not make sense. All right, and then our final question, oops, that kind of looks like two V's, that's supposed to be an I. Try that again. Use the model to predict the distance the ball hit at a 75-degree angle will travel. So let's define that out. A 75-degree angle would mean that x is 75. So we're going to use our model, and we are going to substitute 75 in for all of those x's. So negative 0.17 times 75 squared plus 14.52 times 75 minus 21.79. Obviously, this is a great place to use your calculator or to use your Desmos calculator. You should get 110.96 feet for your answer. Which seems to make sense because as that number is increasing, the distance it's traveling is seen to decrease as well. So 110.96 kind of makes sense with if we're looking at our table or we're looking at our graph.